All right, so we have a little bit of time for discussion before our lunch break. We had some nice discussion during the question sessions about relative contributions of AGN and stars to the ionizing photon budget and output over time. Does anyone want to continue with that discussion? Or are there any other topics that you'd like to talk about?
It just struck me, maybe it's completely nonsense, but it struck me that if you assumed, as you heard earlier today, that the black holes would grow as the galaxies, wouldn't you be expecting to see a similar luminosity function also, if they traced the galaxies, the blue galaxies?
To your question, so my answer is not exactly about supermassive black holes, but on stellar mass black holes, there's well-known correlation ratio between X-ray luminosity of accreting compact objects and star formation rate. So it confirms that at least stellar mass black holes, they indeed correlate very well with star formation rate. It's a Powell law with a well-known slope.
Other thoughts? I saw some luminosity functions in your slides.
It's not really the luminosity function you want, it's the co-moving density evolution, and I think those actually match reasonably well, right? This is the old Hosinger results and et cetera. But for the questions we were posing this morning, and I think as Tim said in his talk, that then is convolved with a number of other things. So it's not that simple either if you're talking about, ionizing the universe. And the one thing Tim didn't mention was the results from fluctuation analysis. Because when you look at different lines of sights, you have different opacities. And then when you do that cumulative distribution of that, you can see that some of that's generated by the existence of large-scale structure, where you have higher densities and higher columns, right? It's harder to ionize. So some of that's explained by that kind of fluctuation that you just naturally get. But then Pierre Medal always makes the point that some of it's not that. There are really intrinsic fluctuations, and those fluctuations then give you kind of what the density of sources you need under some assumptions. And that's also pretty good evidence for the impact of quasars. But again, that's also then convolved to, and Piero makes this point, on what that mean free path is of those photons. And that actually evolves quite strongly with redshift. And then Tim also showed these kind of thermal diagrams of what the background looks like. And if you ask me, probably one of the easiest problems in astrophysics was trying to get the temperature of this kind of diffuse medium in the IGM right. And the funny thing is, it's not, right? So we keep giving people lots of money to keep investigating this, and so we have temperature estimates, but then theoretically to explain it is not so simple, right? Because there's so many parameters that go into it, but it should have been the easiest problem. And what you end up with is the Lyman alpha forest, for example, you end up with these kind of absurd parameters from the models. So these clouds are supposed to be, of the order of megaparsecs in size, which I always found kind of ridiculous because they're shearing. Now there's good theoretical arguments why that isn't the case, but I found these kind of numbers really alarming. So the universe is kind of more interesting than reducing it down to these energy budgets, right? There's a lot more to it than just that, but that's interesting as a first step, but then the rest of it becomes this incredibly hard problem. Why is it the temperature that you observe? And it's still actually quite a mystery. So, and then I guess he didn't also mention that there's this difference in the ionization of absorption lines. I think if you go above about Z of 5, I think it's George Becker's results, you start seeing strong O1 absorption, and that's consistent with a much softer ionizing photon field. And that would suggest starbursts of one kind or another. And that's another piece of evidence on top of all this other things, why it looks like stars, not AGN. But Piero Madawi even doesn't give up on AGN at high redshift, because they have this brilliantly high escape fraction. So I think it's an interesting question itself. Is it low luminosity AGNs? Sorry, I kind of went on long.
While we kind of have disentangled the contributions of the different sources, and we can do this quite well, I think, with the luminosity functions, there are these measurements also from the Lyman forest that you mentioned, that and the ionizing radiation field that you require. There was always like a discrepancy of 2 orders of magnitude or something, if I remember correctly. Is that resolved now, or? So where do these photons come from then?
Anyone want to follow up on that? Are there any other questions that you'd like to discuss?
Hi, my name is Rohan Naidu. I wanted to make a point that was kind of tangentially related to discussions of luminosity functions, and I would call this general category appeals to faintness, right? So a lot of people look at really faint star-forming galaxies and really faint AGN that are way beyond our detection limits to do a lot of work that we are hoping to be done in terms of reionization and stuff like that. And in general, with these beautiful stacking studies that we're seeing in photometric stuff out to redshift 3, redshift 4, I'd like to make the point that to detect Lyman continuum from a source of, let's say, MUV 25, or MUV minus 20, just accounting for the IgM and just assuming some intrinsic ratio for F900 or F1500, take your favorite ratio, let's say 1:5, you need to go 5 magnitudes down your UV magnitude, right? So if you say, I want to measure the escape fraction from MUV minus 20 galaxies, then you need to go 5 mags down. And these are limits that we will never really touch, even with the most wonderful facilities ever. So given that, how do we ever say anything about anything? Even the beautiful Steidl study with all the stacking, Constantina's study that she showed with the beautiful LBT deep U-band images that go down to AB magnitudes of 29, 30, 31, they still give us information only about galaxies that have UV magnitudes of 25, 26, you see, because you subtract 5. But if you're saying all the action is actually happening somewhere else, then we'll probably never really get to it. So then what do we do?
I think that's a good question. Sorry, can you use the microphone? You have a different question? Yeah. Does anyone want to address this? Ryan?
So I'll talk a little bit. Yeah, this is something I think about a lot because I think, I'm trying to, look at the fainter things and what Chuck is doing, and so I don't think we can do that directly, and so I think we rely a lot on the work that a lot of people are doing here. You're looking at, I'll talk a little bit about some of the results from the Steidl paper today to maybe clarify some of the points that are buried in the 40 pages of the paper. But I think in general, looking at some of the relations that we see between, escape and other things, as Francesca has shown in her recent paper, and others, that if you look at the trends, then we can find other things that are good predictors. And I think that's what we're all looking at, or what other things, predict Lyman continuum in the case that we can't see. Because even if we could go down and say, really measure Lyman continuum from dwarf galaxies at redshift 3, we're not going to do it in any galaxies at redshift 7, and that's what we really want to know about. So, the same tools that we're going to use to predict, across changes in magnitude, hopefully will be useful for predicting across changes in time. So I think the correlation with Lyman alpha is really interesting. That's seen in Francesca's paper. It's seen in our paper. It's been predicted in theoretical models. So I think in the redshift range where we can see Lyman alpha, that's a useful tool. And then as we push back to the, the regime where we can see neither Lyman continuum nor Lyman alpha very reliably, that these other kind of secondary tools will be very useful.
Armin, did you still have a question? You were first.
Okay, so I have not actually polished this idea. It just came to me just maybe 1 hour ago. So maybe this is actually also a question which can be like from different fields. So I know that until 1 or 2 years ago, we didn't have any clear evidence for intermediate mass black hole. And also having the talk today, I learned that the escape fraction for the AGNs can actually be, for the Lyman continuum, can be actually quite high from the black hole. So I don't know if there is any constraint that we can have from studying these clumps at high redshift to put any constraint on the existence of intermediate mass black holes. Because as also Angela's talk pointed, we know that some of these clumps can actually also be the future globular clusters that we have. And actually people were always looking for these intermediate mass black holes in the globular clusters. So I don't know if this can also, having also this intermediate mass black hole can also contribute to this Lyman, to the reionization of the universe, perhaps. So I don't know if anyone has any thoughts on this.
I think that's an interesting question, and it relates to questions that I have about how all of you who work on AGN might be able to help us advance a little bit, those of us who work on galaxies, to try to quantify what contributions there might be at a very low level from things like very low mass black holes. Thoughts? Other questions, topics? Alice?
Question related to the talk by Maxime. So, if I understood correctly, the result of his models, he finds theoretical evidence for an asynchronous evolution of the supermassive black hole and bulge or galaxy. So basically, it breaks down at some point. Low mass galaxies do contain intermediate mass black holes, or anyway, they are unevolved. Whereas at some point, perhaps after 10 to 10 solar masses, above 10 to 10 solar masses, you have the standard supermassive black hole bulge or galaxy correlation, right? What are the, is just the supernova feedback that prevents at the low mass end of galaxies to develop a supermassive black hole?
So that's what I see in my simulations, but again, they are just simulations, so they are by no means realistic representation of reality as we could see it. I mean, it's the best we can do, but we don't resolve the very small scales near the black hole. So that's what I can tell from my simulation, and other groups see similar things. But that's, again, I guess the main problem is we don't know how supermassive black hole form at all. And we don't really know why they grow efficiently, because you have to bridge like the scales, the accretion disk scale all the way to the galactic scales. And in simulation, that's effectively impossible to do. So all we can do is rely on like subgrid models for one or the other scale, well, subgrid or like large scale assumptions. So I mean, it's work in progress, but I'm not sure we can tell much yet about that. So all I'm doing in my simulations, for instance, is I'm assuming that there is a black hole in that galaxy, but the fraction of dwarf galaxies that host massive black holes, it's not clear at all. And I don't want to say that they are intermediate mass black holes, because when I say that to black hole and AGN people, they say, oh no, they're not intermediate mass black holes. They're like low mass supermassive black holes, which is a bit weird to me. But that's the thing. I mean, it seems that it's two very different communities, and having the two talk together, I have a hard time doing that.
Well, one question is whether the physics that you are exploring with your models are applicable after some modifications also to bulges, for example, galaxy bulges. So we know, for instance, that low mass bulges in almost bulgeless galaxies or disk-dominated galaxies do not show signatures of the strong AGN activity. So the BPD diagrams, they appear, they fall in the locus of star-forming galaxies. And that was also a paper by Iris Preta analyzing Khalifa galaxies, and find this result that all low mass bulges are star formation dominated, and accretion power nuclear activity becomes important above a critical mass of 10 to 10 solar masses, as also other studies are showing. It's not the first time. But what's happening? Why in the low mass regime of bulges, it happens that the supermassive black hole does not manifest itself, if existing, as an AGN? I think this is one mystery. Is it a sporadic accretion of matter or other reasons why they do appear as star-forming?
So I guess the short answer is I don't know, but what I can tell you is, I mean, the galaxies I'm simulating, they don't have bulges, and I mean, usually we look at the black hole mass to stellar mass relation as black hole mass to bulge mass or velocity dispersion. And in the low mass regime, it's not very obvious that it's still the right indicator to look at, because dwarf galaxies don't always have bulges at all. The velocity dispersion doesn't necessarily trace the same thing as doesn't trace the central mass. So that's, people start to look in the low mass regime at black hole mass to total mass, but then it's not easy to explain why that should be correlated at all, because again, the black hole reacts in the center and the total mass is more extended. So, yeah.
Okay, I have one more question, a small one. I see so many studies exploring the Lyman continuum escape fraction from star-forming galaxies, indirectly, not a direct detection, but on the basis of a model. So that they make the numbers, that they compute the Lyman continuum production rate, the intrinsic one, and by comparison of nebular emission lines, the observed ones with the predicted ones, they get an estimate of the Lyman continuum escape fraction. How is the intrinsic Lyman continuum production rate estimated? This also led to the talk by Miguel. This presumes an understanding or a good estimate of the star formation history. Or am I wrong? To estimate the intrinsic Lyman continuum production rate, you need to know the star formation history. What assumptions are made in this respect?
What's your question about what kind of objects? What's your question?
How can we estimate the intrinsic Lyman continuum production rate in a star-forming galaxy?
Star-forming galaxies?
Yeah, so we have to know the star formation history, right?
No. If we want to know the Lyman continuum production, we need to be able to quantify how many stars emit UV radiation. So for this, you can either just observe the UV continuum, or you can do more clever. You can do what different people recalled you in the
the first few days is you can measure the radiation which is absorbed in the nebula, which comes out in recombination lines, right? So whatever are the sources, you will recover ionizing photons. You can count them if they are absorbed in the galaxy. So just H-alpha, I mean de-reddened recombination line fluxes. And then you measure what comes out in the Lyman continuum, and the sum of the two is the total amount which is produced. And the fraction of 1 over the total is the escape.
Okay,
that's basically
yes, but
relatively straightforward in principle.
But the UV luminosity at 1,500 angstrom would not raise only the very young stars, but could also give an estimate of B9, B8 stars, so with an age of 90 million years. Can we, from the UV luminosity, be sure that we capture also the Lyman continuum output from the very young stars with younger than 10 million years? Because these are producing probably most of the Lyman continuum.
Sure, but I mean, with the observables, I'm saying you don't know what are the sources. You just count the photons. So of course you cannot say which stars produced it, but you can count and you can measure the escape fraction. So if you're interested in this question,
okay, we can discuss.
But you count only the sources that when you measure the escape along the sidelines. So there might be escape along different sidelines or not. Sure. So there's a bias in this calculation.
Sure. Yeah, it's not saying. Sure, it's
But when you estimate the escape fraction along this sideline, you also overestimate the global escape fraction from the same galaxy. So I think that these, if you have a statistically large enough sample, these two effects will cancel each other, right?
One question, and I think one problem that is not tackled in all, to my opinion, in all simulations is, for instance, we only consider the Lyman continuum photons from the stellar component, but we know, for instance, when supernova explodes, they lose their energy by PDV work or so. So this means they can cool down very rapidly to 10 to the 5 degrees, a little bit, or several 10 to the 5 degrees, where they cool also efficiently. And these photons also contribute, for instance, to the Lyman continuum, even to the Lyman edge, and that is, to my opinion, never taken into account. And I do not know any study where the Lyman continuum radiation from the stellar component and of these, let's say, Lyman continuum post star formation component is taken into account. And to my opinion, that should contribute also to the reionization in the universe, because in the expansion also then you shift the hot Lyman continuum photons to the soft part, and that also contributes to the ionization.
This is a very nice reply because I actually do that in my simulations. So I look at the stellar component of the star formation rate they produce. You have this shock heated ice, and the interstellar medium produced like a diffuse component of the Lyman continuum photons, and then they have a very different spectrum than the stellar component, because the stellar components that reach near the ionization threshold of hydrogen, but the ISM photons on the other hand, they have like almost a polar component. It looks like an AGM and much fainter. But the interesting thing I see in the ionizing RT simulations I'm running is that they heat the medium much more efficient than the stars. So that's one signature you can look for. But they also were thought to be, could be degenerate with the X-ray binaries, because the X-ray binaries also produce X-rays, so it could be heating. But the interesting thing about X-ray binaries, the contribution to Lyman continuum photons from them, is that they're much harder. They're like up in the keV scales. So that's an interesting component you take up there, the Lyman continuum production from the shock heated gas.
Just continue with this. Indeed, in our models in Cerviño Masgese some years ago, we also considered the ionization in the Lyman continuum by this effect, by the ultimate mechanical energy which has been released by the starburst and has been converted into ionizing luminosity. So in a way, this has been considered. And indeed, This was mentioned today or yesterday, I forget. This has an effect on the H2, the helium-2, sorry, emission intensity. It is not enough to reproduce the helium-2 H-beta ratios that we see, but it can at least partially contribute to them. And concerning what Daniel Echeret said, he's right, and Polis is also right. So in principle, from the UV continuum, we can derive what is the intrinsic ionizing continuum. But as Daniel said, but as Polis said, we have to make some assumptions, at least some minor assumption about the star formation regime. It is for the same value as I demonstrated on the first day. For the same value of the UV continuum, we can have quite different values of the ionizing continuum. So in a way or the other, you have to constrain what is your evolutionary scenario. Otherwise, there is a degeneracy there, which is significant.
Are there any other burning issues you'd like to discuss before the lunch break? All right, well, why don't we thank all of our speakers for this morning. And we'll reconvene at lunch and at 4.